Welcome to qnawire.
This is problem number 14 of chapter 23. This problem makes reference to problem number 13, so let's just do problem 13 really quickly and let's answer the question of 14. So the setup for problem 13 is we are given the second order deflection angle, so theta sub 2 is equal to 38 degrees. We are also given the wavelength. Lambda is equal to 680 nanometers. So let's go ahead and convert that to meters. With this information, we are asked to solve for the number of lines per centimeter. So to do that, we're asked to solve for n. To do that, we must solve for d because 1 over d is n. So to solve for that, recall the formula d sine of theta m is equal to m lambda for constructive interference. So here we're talking about the second order deflection angle. So this is the angle at which the second right fringe is found. So we would plug this in with m equal to 2 here. We have m, which is 2. We have lambda here. And all we have to solve for is d. So d is going to be equal to m lambda over sine of theta m. The n that we're looking for is just going to be the reciprocal of this. So we could go ahead and solve for that directly. N is going to be equal to sine of theta m over m lambda. And in this case, in this particular case, we know that m is equal to 2. So let's go ahead and solve for this. It's going to be over 2 times lambda. And the answer, the units here for this quantity is going to be in inverse meters, or it's going to be in lines per meter. So when we calculate this, we get approximately 452,692 lines per meter. And let's convert this to lines per centimeter. So for lines per centimeter, we're going to have to go ahead and multiply this by a conversion. So 1 meter is equal to 100 centimeters. So we're just going to go ahead and move the decimal place 2 times to the right. Actually, no, 2 times to the left. So 1, 2, it would be right here. And let's round to the nearest whole number. It's going to be 4,527 lines per centimeter. Now this is a rate, number of lines per centimeter. So now we could answer question number 14. Question 14 says if half of the lines of the grate, if the grating, half of it breaks off, what's going to happen in the diffraction pattern, in an interference pattern? Well, as we talked about before in a previous problem, when we have a diffraction grating, it causes narrow bright fringes and wide dark fringes. So on our screen, we expect to see a pattern like this. We expect to see bright fringes that are narrow and wide dark fringes, like so. Here, the distance between this endpoint and this screen represents the intensity. In reality, what you would see is something like this. On the screen, you would see these bright spots like this. you would see bright spots and wide, dark fringes. The more lines or the more slits you have in the diffraction grating, the brighter these lines become. That won't affect their location, because here, if we go to the grating itself, the grating is going to be here. So let's draw the grating. Let's suppose this is the whole grating, and here are a couple of the slits in this diffraction grating. Suppose these top two, actually let's do this one. Let's suppose these two openings go to one of these minima here. And again, this screen is so far out that the slopes of these two light rays are parallel. The path length difference between these two is going to be an integer multiple of the wavelength for constructive interference. Now, the next lowest grating, the next lowest slit in the grating, let's go ahead and draw it like this. The path length difference between it and the one above it is going to be also an integer wavelength. So all these three are in phase and so far down the line. So all of the openings in the diffraction grating are in phase with respect to the bright fringes. If I eliminate, so you can imagine a lot of slits here. Notice that we have around 4.5, 4,527 lines per centimeter. So that's a lot of lines. We have, if we eliminate half of them, so half of the grating breaks off, we still have more than enough lines for constructive interference to occur. As we include more openings, what that does is it makes the bright fringes brighter. It doesn't alter their location. So by breaking half of this diffraction grating off, you aren't changing the pattern here. The intensity might go, it will go down, but the pattern itself, the location of the fringes, will be exactly the same. So that answers questions 13 and 14.